Hi folks, this is Heath. We're starting section 14.6 today, which is on directional derivatives. A couple of reminders at this point. There is a new web assignment. It's the Review 7 assignment. It goes up today and it will be due in a week. It will be due next Thursday night. So please don't forget to do that. Let's go ahead and get started with this section. So far we have looked at examples of derivatives rates of change in the x direction, which we call dz dx, and in the y direction, which we call dz dy. But what if we want to find the rate of a change in a diagonal direction, in the direction of one of these vectors, for example? That's what we're going to cover today, is how do we find the rate of change in the output value of a function if the input is changing in a direction that's not exactly the x direction or the y direction. Okay, so the idea is, based on things that you already know, that we're going to calculate a rise, we're going to calculate a run, and we're going to divide them together to get an answer. So we're measuring rise over run, and we've covered the two special cases, the derivative in the direction of the x-axis and the derivative in the direction of the y-axis. If it's in some diagonal direction, then we have to calculate how much of the change was in the x direction and how much of the change was in the y direction. That the diagonal direction will have some x and some y component to that direction, and we'll have to combine those together. But combining them together is easy. It's just multiplying and adding. It's something you've done already before. So let's go ahead and get started. Let's look at an example. We have a hiker who is standing at the origin along a terrain that has this contour here. X squared minus 2x plus 3y. Where x and y and z are all measured in meters. This terrain is mapped here below. The hiker is traveling along a path that lies 45 degrees between the x-axis and the y-axis. And we want to describe how steep the terrain is as the hiker is moving in this direction. That's going to be the idea. Okay. So the first step we're going to do is take the two partial derivatives of the function. So find out what the change would be in the x direction, and that is 2x minus 2. And since we're at the origin, x is 0. And so we get negative 2 for the partial derivative for x, and we get just 3 as the partial derivative for y. Excuse me. Sorry about that. All right, so now we have some partial derivatives here. The other thing we need to do is find a direction that the hiker is traveling. And so we need a vector that travels at a 45-degree angle between the x-axis and y-axis. Any vector will work. I'm going to use 1, 1 as my direction vector. But we could use 2, 2 or 3, 3 or 4, 4. Changing the size of the vector will change the amount of the run in the rise over run calculation. But that's okay. We can pick any vector that moves in that direction. All right, so let's talk about what happens now. We're using the vector 1, 1 to represent the direction at a 45-degree angle from the x-axis. And so the traveler went, or the hiker went 1 unit in the x direction, and when the hiker went 1 unit in the x direction, the slope went down by negative 2. But then the hiker went 1 unit in the y direction, And when you go 1 unit in the y direction, the slope goes up by +3. And therefore, the total rise is -2 and +3 is 1 meter. Okay? What we have done here is technically we've taken a dot product. We took the dot product of the vector 1, 1, which was the direction, and the vector -2, 3, which are the partial derivatives. Okay? 1 times -2, we went 1 step in a direction that took us down 2 units, and then 1 step in a direction that took us up 3 units. So 1 times -2 plus 1 times 3. And that gives me the rise. So we went down 2 units by moving in the x direction. We went up 3 units by moving in the y direction. The net change is that we went up by 1 unit. Now we have to calculate the run. Well, the run is the magnitude of the vector that we chose. If I start at the origin, 0, 0, 0, and I run 1 unit in the x direction and 1 unit in the y direction, then the distance is the square root of 1 minus 0 squared plus 1 minus 0 squared plus 0 minus 0 squared, which is the square root of 2. This is just the distance formula. It's how far we traveled along the xy plane. Okay? So that's the run. It's just a distance formula. It's what the length of this vector is. And so we have the rise and we have the run. And so the directional derivative, the slope, is rise over run, which is 1 over square root of 2, which is about 0.707, which means the physical interpretation here is that as a hiker moves forwards, the elevation increases at a rate of 0.707 meters for every meter the hiker has traveled forwards. If you want a comparison for how steep that is, it's slightly steeper than a normal flight of stairs. Typical flight of stairs has a steepness of about 0.6. Okay? All right. So what we did was we calculated the vectors of the partial derivatives, and we took the dot product of that with a direction vector, and we got the rise. Then we took the magnitude of the direction vector, and we got the run, and then the directional derivative. In other words, just the derivative in this direction is the rise divided by the run. I did this notation down here at the bottom. We'll talk about that notation in a moment. So some notes in the process. Sometimes we will pick a unit vector for the direction vector, because then the magnitude of the direction will be equal to 1. So if D is a unit vector, the magnitude is equal to 1, and so the directional derivative is D times Fx, Fy. Okay? The notation that we use for a directional derivative is the derivative in the direction of v of the function f. So it's a capital D for a derivative, a little v for the vector in the direction we're traveling, and then an f for the function. Okay? And we abbreviate this vector of partial derivatives that we used right here in the calculation. We call this the gradient vector. and the symbol for it is an upside down delta along with an F. So we can abbreviate this formula here. Over here I use V instead of D for the vector. V times the gradient vector delta F, that's a dot product over the magnitude of V. And again, if V is a unit vector, then it's just the dot product. And the book prefers to always use unit vectors for V, but you can actually do this with any vector. Okay? So let's try another example. Let's find the derivative of this function at the point 1, 2 in the direction of the unit vector. We're going to use a unit vector for this example. 1 over root 2I plus 1 over root 2j. Okay. So the steps here, we need to know the partial derivatives for this function. And so the partial derivatives are 2x plus y, and the derivative in the y direction is just x. Our point is 1, 2. So at the point 1, 2, this is equal to 4, but this is just equal to 1. And so the gradient vector is the vector for 1. It's just a vector of partial derivatives. That's what we got here. The direction vector is given to us. It's, and they use u for this, 1 over root 2 and 1 over root 2. And so the derivative in the u direction of the function is 4 over root 2 plus 1 over root 2, which is 5 over root 2. We don't have to divide by the magnitude of u because we know that magnitude is 1 since they gave us a unit vector. And so we just calculate the dot product of these two vectors and we have the directional derivative. Okay. So directional derivatives aren't hard. They combine what we know about regular partial derivatives with a dot product operation. Let's keep going. Let's try a few more examples. Let's find the derivative of this function and the direction of the vector 3i minus 4j. Okay. This problem is similar to example 2, but the direction vector has length 5 and not length 1. That should be a 1. This is not a unit vector, and so we'll have to divide by the magnitude of this vector when we're finished. Okay, so let's give this a try. We need the partial derivatives, fx and fy. The derivative here is, with respect to x, is just e to the y. Derivative of x e to the y becomes 1 e to the y. And then derivative cosine of xy is derivative cosine is negative sine. And then we multiply it by y. Then the derivative in the y direction, the derivative of x e to the y is still x e to the y. The derivative of cosine becomes negative sine, but this time we multiply by x. And since we're at the point 2, 0, this is e to the 0 minus 0 times the sine of 0. And this is 2 e to the 0 minus 2 times the sine of 0. Well, sine of 0 is 0. Sine of 0 goes away in both cases. E to the 0 is 1, and 2e to the 0 is 2. And so my gradient vector is 1, 2. And so the directional derivative, the derivative in the direction of v of the function, is the dot product of 1, 2 and 3, negative 4 divided by the magnitude of this vector 3, negative 4. The dot product is 3 plus negative 8 is negative 5. And the magnitude of 3, negative 4 is 5. That's a 3, 4, 5 triangle. You should recognize that without having to work out the calculation. But the derivative turns out to be negative 1. So if we're walking forwards in the v direction, the elevation is going downhill as we walk forwards at a rate of 1 meter for every meter we travel. Okay? Let's keep going. Number 4. The same principles apply for finding directional derivatives in higher dimensions. I just have 3 inputs now. So let's see how this is going to work. The derivative in the x direction is 3x minus y squared. Derivative in the y direction is negative 2xy. And the derivative in the z direction is minus 1. And since we're at the point 1, 1, 0, this is going to be 3 times 1 minus 1 squared, which is 2. This is going to be negative 2 times 1 times 1 is negative 2, and this is negative 1. And so my gradient vector is the vector 2, negative 2, positive 1. And so the directional derivative is the gradient vector 2, negative 2, 1, dot product the direction vector divided by the magnitude of the direction vector. And that is, what is that? 2 minus 2. The numerator is 0, is that right? And the denominator is square root of 2, but that doesn't really matter. The derivative is 0. What is that saying when we travel in the direction of crap? Sorry about that. Let me back up a little bit. I was surprised when we got 0. This is the direction vector. 2, negative 3, and 6. Let's try that again. Sorry about that. Stupid. All right, let's keep going here. 2 times 2 is 4. Negative 2 times 3 is 6. 1 times 6 is 6. That gives me a 16. That's better. And then the magnitude of this vector turns out to be the square root of 49, which is 7. There we go. That's the correct answer, not what I had before. Okay. All right, we've got a couple minutes left. Let's look at a couple of additional properties that we haven't talked about the gradient vector. It turns out that if we draw, and we've seen this before, this map of level curves. We did this back in section 14.1, where we set z equal to a bunch of different constants and plot the level curves at that point. It turns out that at any point, the gradient vector will be tangent or perpendicular to the tangent to a level curve. So this light blue curve is a level curve. This dark blue curve is the gradient vector. And the tangent to this level curve at this point, these are perpendicular to each other. That's sort of a surprising little piece of information, but it means that you can sketch the direction of a gradient vector immediately without knowing any of the details. If I want to find what the gradient vector looks like at this point here, well, the tangent line looks like this, and so the gradient vector has to look like that because it has to be perpendicular. I don't know how long it is, but I know the direction of the gradient vector. If I want the gradient vector at this point here, that's a tangent line, so the gradient vector would be moving in that direction. Okay? That's the idea. So the gradient vector is always perpendicular to the level curve at any point where the gradient vector is being calculated. Another piece of information we would like to know is that the gradient vector gives us the direction in which the directional derivative is the greatest. From the point of view of the hiker, if I wanted to travel in the steepest direction possible, which direction can I travel if I want to make the hike as challenging as I can? I would travel in the direction of the gradient. The gradient always points to the steepest direction. This is useful if we need to affect rapid change in the system. For example, if we have a function that measures the temperature of a system, and that temperature has exceeded a safety margin, we might want to cause that temperature to drop, and we'd like to drop it rapidly because we have exceeded a safety margin. We need to get that temperature back down. And since we want the direction that moves the fastest, the steepest descent in temperature, because we're looking for a descent instead of an ascent, then we'll take the direction opposite the gradient vector to accomplish this. And so if I want to know how to change x and y to relieve that excess temperature as fast as possible, I would adjust x and y in the direction opposite to the gradient vector, and that will move it down quickly. Okay? All right, so let's try a couple of examples then. Find the direction in which this function increases most rapidly at the point 1, 1. Well, that would be the direction would equal to the gradient vector at that point. And the gradient vector is the partial derivative of the vector made up of partial derivatives. Okay? All right, so the partial derivative in the x direction is x. Oh, and the partial derivative in the y direction is y. And so x is 1 and y is 1. And so the vector that we want is the vector 1, 1. So if we're at the point 1, 1, and we want to increase as rapidly as possible, we also want to move in the direction 1, 1. That direction will create the fastest increase in height. Okay? Let's keep going. Last example. Let's find an equation for the tangent line to this ellipse here. X squared over 4 plus y squared equals 2 at the point negative 2, 1. Okay? So let's kind of sketch what's going on here. X squared over 4 plus y squared over 2. So the intercepts in the x direction will be at the square root of 8, which is between 2 and 3. And the intercepts in the y direction are at square root of 2, which is between 1 and 2. And negative 1, negative 2. So that's the ellipse we're looking at. At the point negative 2, 1, we want to find an equation for this tangent line. Okay? One way we could find a slope is by using implicit differentiation. And we know that. But here's another trick we can think about. This is, so let me first mention one way is to use implicit differentiation to find the slope. But this is a tricky way that we can use sometimes. It might sometimes be faster. This is a level curve therefore, x squared over 4 plus y squared equals z. That is the way we find level curves, and we replace z with different constants. And so this is a level curve for x squared plus y squared equals z. And so the derivatives of this function are, bring down the 2, let's see, this is x over 2, and derivative in the y direction is 2y. And at the point negative 2, 1, this is negative 1, and this is positive 1. No, positive 2. And so the gradient vector for this function is negative 1 and positive 2. So the gradient vector is pointing in the direction negative 1 in the x direction and positive 2 in the y direction. That's the direction the gradient vector is pointing. Well, we know the gradient vector is perpendicular to the tangent line. The slope of the gradient vector is the change in y over the change in x, which is 2 over negative 1, which is negative 2. And so the slope here is the negative reciprocal. Which is positive 1/2. So we could use the slope of the gradient vector and then take the negative reciprocal and get the slope of the tangent line, instead of having to use implicit differentiation. Is that faster or not? I don't know, but it's a different way of doing the problem. Okay? And so now that we know the slope is 1/2, we can use point slope form. Y minus 1, that comes from this point here, is equal to 1/2 times x plus 2. The plus 2 comes from that term there. And that gives us an equation for the tangent line without ever having to actually calculate the implicit derivative. We calculated the gradient vector instead and took the negative reciprocal of its slope. All right, y'all take care. Have a fantastic weekend. Take care.